Okay, hi guys. Today we are moving on to tests of significance for means. Like confidence intervals, means are much easier with tests of significance. I guess we just saved the easier one for last. So let's just jump right in. The Energizer Battery Company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on her experience with graphing calculator usage, Mrs. Sims knows that regular AAA batteries last for 30 hours of continuous use. She takes a random sample of 30 new batteries and finds that they last for 33.9 continuous hours, and they have a standard deviation of 9.8 hours. Let's run a significance test with a significance level of 0.05 for this data to see what you would think I could figure this out. Mrs. Sims, not Ms. Hurley, can conclude from her experiment. So, just like we did with one sample percents, with one sample means, our null hypothesis will be, in this case, mu equals some claimed value. That'll be the 30 hours. Okay, now they are claiming to have developed a new AAA battery that lasts longer. So our alternate will be that mu is greater than 30. And just purely based off of the sample, it seems like that might be true, right? Because the sample mean was 33.9. So now our three conditions for means: random, yes, right? She took a random sample where n was 30. Independent. Oh my gosh. Yes, because 30 is definitely less than 10% of all batteries. And normal. This one's so much easier. Yes, because n, which is 30, is greater than or equal to, it is equal to 30. All right, and so just like we did with percents, we're going to have a test statistic. That test statistic is going to measure how far a sample statistic diverges from what we would expect. This test statistic is going to be a t-score. Remember, with means, we use a t, like t inverse t, for our critical value. So we're going to use that as well here. And so we will say our statistic x bar minus the parameter mu over our standard deviation, which is s over the square root of n. Now just to confirm that on our formula sheet. Now we're down here looking at means. And we're sitting right here, s over the square root of n, right? For one population, not two. So find that test statistic. T equals x bar was 33.9 minus the claim value 30 divided by the standard deviation 9.8 over the square root of 30. All right, so we know we'll have 3.9 up top. And we get 2.1797. Now, I've been a little inconsistent on my rounding for this test statistic. In general, I think we could round to 2 here because it's like a z-score or a t-score. Whereas those percents that you were getting, we went 4 decimal places because ultimately you move it 2 decimal places to make it a full percent. So that sort of explains why I've been inconsistent. Now, this test statistic says how far the sample result is from the assumed null hypothesis value. So it is 2.18 standard deviations above the value. So now here's our normal curve. Right, centered at 0. We've got 2.18. We shade to the right because our alternate up here said that mu is greater than 30. And so we use the sketch to find the p-value instead of normal CDF because we had a z-score. Now we're going to do t-CDF because we have a t-score. In t-CDF, if you hit second vars on your calculator, it is option 6. It still asks for a lower and an upper. So 2.18 to a positive 1,000. But now remember, degrees of freedom are equal to n minus 1. So in this case, we'll have 29 degrees of freedom. Okay, so 2.18 to 1,000, 29 degrees of freedom is 0.01875, so 0.018. Maybe instead of 7, we'll do 8 because it's got a 5. Now that value, we set our significance level for 0.05. That value is less than 0.05, so we can reject the null in favor of the alternate HA. Well, so what's that mean? If we're favoring HA, that means this is our conclusion, that mu, the mean, is longer than 30 hours. Right? Okay. So this sort of pulls everything together. When we choose a simple random sample of size n from a large population, we test our hypothesis that mu equals some value by using a t-score. Right, remember, degrees of freedom are equal to n minus 1, and we shade exactly the way we have been. So if it's greater than, we shade to the right, less than to the left, not equal to, we shade in both directions. Okay, so example 2 says, the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. Dr. Smith is sure that the stream behind his house will support aquatic life. He claims that the level of DO is always below 5 milligrams per liter. He measures the dissolved oxygen level at 30 randomly chosen locations along the stream and finds a mean of 4.98. That's our X bar, and a standard deviation of 0.92. Run a test of significance using a significance level of 0.05 and calculate a 95% confidence interval to support your conclusion. So in this case, we know X bar is 4.98, where N, his sample size was 30, and we are looking at the average dissolved oxygen level in the stream. We're going to let alpha, our significance level, be 0.05. Oops. Where our null hypothesis will say that the mean, the actual population average for the whole stream, is equal to 5 milligrams per liter. And the alternate will say his claim that it is always below, so less than 5 milligrams per liter. All right. He did take a random sample. He did ensure that they are independent trials or samples because 30 spots in the stream is less than 10% of all. In this case, he sampled locations in the stream, so it would be less than 30% of all locations. In the stream. All right, and then normal. This is where it saves us time. Normal, yes, because 30 is equal to 30. Okay, so now we can move on. Our test statistic, T, will be equal to our sample mean, X bar, which was 4.98. Minus our claimed mean of 5 divided by our sample standard deviation, 0.92 over the square root of 30. All right, well, we know this is going to be negative because 4.98 is less than 5. Divided by the square root of 30. Oops. Is negative 0.1191. So on our curve, we'll notice that's like barely below 0, which we could have predicted because 4.98 was so close to 5. we are shading almost half of our curve, which means we should anticipate a pretty high p-value here. So we would do TCDF to find this p-value from negative 1,000 to negative 0.1191 with 29 degrees of freedom. So second vars, TCDF is option 6. I get 0.45. Yes, a very high p-value. Right, 0.45 is absolutely higher. Our alpha level was 0.05, so absolutely greater than 0.05. So we fail to reject the null, meaning that our test is inconclusive. Okay, again, what does that mean? Well, it means we can't say for sure that the level of dissolved oxygen in the stream behind his house is less than 5 milligrams per liter. So now we're going to do a 95% confidence interval, CI, where we start with our X bar value. Then we have a t-score as our critical value times that sample standard deviation over the square root of n. So X bar was 4.98 plus or minus, we'll say inverse T. Now remember, inverse T is in that second vars menu. It only takes the area to the left. So if we're doing a 95% confidence interval, then we have 95% in the middle, so 0.025 on either side, 2.5%. And then the second number it takes is our degrees of freedom, which was 29. Okay. So negative 2.045, 2. So plus or minus 2.0452 times 0.92 over the square root of 30. Okay, so this is 4.98 plus or minus 0.3435. Okay, so 4.98 minus is 4.6366. So I'll just say 4 to 5.32. And that is milligrams per liter. Now this gives us our problem. Remember, we said it was inconclusive, meaning we don't know if the mean is actually less than 5. And that is further emphasized by this because part of our interval is higher than 5. And so this interval shows that that level of dissolved oxygen might actually be higher than what he thinks it is. And so that's why our test resulted in an inconclusive answer. All right, so go ahead and give this, I think I gave you 2 practice. Yep, 2. So see how you do, and we'll talk to you soon.